Welcome to the exercise lesson on the definition of limits. Today, we'll discuss about the types, solutions, and some of the examples of limits calculation problems you might encounter during calculus. I'll first introduce you into different types of limit calculation. There will be no value table included, as this video will focus solely on solving limits algebraically. The first type is rather the easiest one, direct substitution. As from the lesson video, you know that in order to solve for a limit at point A algebraically, we simply substitute A into the function. This is the case here. This is usually the case where you only have to deal with polynomials. Okay, so let's jump into examples, shall we? I have here is the limit of 3x squared plus 5x minus 9 when x approaches 3. So how do I do this one? This is rather pretty simple, and it is as easy as it looks. Because whenever you try to plug any number into a polynomial, just a polynomial alone, without fractions or any more complicated form, it will always result in a real and defined number. Now, isn't that nice? Because basically with every a number, you have to find the limit at. You just need to plug a into the function itself and then calculate. Now, let's see how this one goes. I'm going to try to plug 3 into the functions. It's going to be 3 times 3 squares plus 5 times 3, and then minus 9. This one is just going to be equals to 27 plus 15 minus 9. And then we have the final result is just 33. Another one just involves substituting number is going to be the limit of 4x cubed plus 3x squares plus 2x plus 1 when x approaches 2. Because this is also a polynomial, it should be also just substituting number into the function. It's going to be 4 times 2 cubed plus 3 times 2 squares plus 2 times 2 and then plus 1. And it's going to be 32 plus 12 and then plus 4 and plus 1. With simple calculation, it is just going to be equals to 49. The second type will be a little harder because it requires an additional step, factoring. Some functions requires to do this extra step because if we try to just substitute, the limit will not be defined like the previous type, but rather in an indeterminate form. There are 7 indeterminate forms in total. 0 over 0, 0 times infinity, infinity over infinity, infinity minus infinity, infinity to the power of 0, 0 to the power of 0, and finally 1 to the power of infinity. However, you most likely just encounter 0 over 0 in calculus 12. Normally, factorizations of functions will help you to create a new form of that same functions. However, when you try to substitute a into that new function, it will result in a determinate form, a defined value. This type of limit calculation will usually involve fractions with both numerator and denominator as polynomials. I have this classic example that will show you how factorizations help you to avoid indeterminate forms. For this one over here, limit of x squares minus 4 over x minus 2 when x approaches 2. Okay, so as you try to substitute 2 into the functions, the limit would just be equals to 0 over 0. I'll do it right now. It's gonna be 2 squares minus 4 over 2 minus 2, which is just gonna be 0 over 0, which is not possible in mathematics, right? So the limit, that's obviously not defined, and so I've somehow managed to change this function so that my denominator would not be equal to 0. This is where factorizations comes into play. By now, you probably have seen where I should factor. Here, the numerator can easily be separated into brackets using the difference of square formula. I'm going to start doing it by the aforementioned method. So, I would try to just simplify the numerator over here. I mean, by factoring it, it's just going to be equals to x squared minus 2 squares over x minus 2. And that's the difference of squares formula you see over there. It's gonna be x minus 2 times x plus 2 over x minus 2. So you see over here, x minus 2 in the numerator should cancel out x minus 2 in the denominator. Hence, the function now has an entire new form of x plus 2 only, and when you plug 2 into the function, it would just be equals to 2 plus 2, and our limit is now completely defined and equals to 4. Another example would be the limit of x squares minus 2x minus 15 over x minus 5 when x approaches 5. And when you try to plug 5 into the functions, again, it would equal to 0 over 0, which is a indeterminate form, and you can't do that. So I'll try to factor the numerator, but not by using the difference of squares formula, because I cannot do that here. I'm going to try a different way. And I think you know that already. It's pretty simple. I would just take negative 2x and turn it to negative 5x plus 3x minus 15 over x minus 5. And I'll group x squares with 3x and negative 5x with 15 with negative 15. What I have will be x and then times x plus 3 minus 5 times x plus 3 over x minus 5. It is going to be equal to x minus 5 times x plus 3 over x minus 5. And obviously, x minus 5 will cancel each other out. And what I end up with is going to be just x plus 3. And it is now very simple. Plug 5 into the functions, and what I have is just 8. A more complex problem could be finding the limit of x squares minus 11x plus 24 over x squares plus 9x minus 36 when x approaches 3. And again, you can't just substitute 3 into the functions. You have to find a different way. And in this case, you have to factor both denominator and numerator in order to get our limit. So I'm going to do both. I'm going to factor both numerator and denominator at the same time. X squares, negative 11x. I'm going to turn it into negative 8x minus 3x plus 24. X squares, and then from 9x, I'm going to turn it to 12x minus 3x. And then minus 36. I'm going to group them together. This one with this one, this one with this one, this one with this one, and then this one with this one. It is going to be x times x minus 3 minus 8 times x minus 3 bracket, and then x bracket x minus 3, and then plus 12 times x minus 3. Now you see the pattern, right? I have 4 brackets in total across the whole function. And obviously, x minus 3 will cancel each other out. And what I end up with is a very simple functions that when you try to plug 3 in, it's not going to be equals to 0 over 0 anymore. But rather, it would be negative 1 over 3. The third type that usually appears in Calculus 12 is complex fraction. A complex fraction is a fraction that has fractions in the numerator, denominator, or both. Like the previous type, it won't let you just substitute. You'll have to simplify the complex fraction to make it a completely normal fraction. You can do so by first simplifying the numerator, denominator, or both. Depends on which contains extra fractions. By combining the extra fractions in the numerator or denominator or both, by adding or subtracting them depending on the operation. After that, some will just cancel each other out, and be sure to look for it. And finally, you'll have an entirely new function, one that when you try to substitute a into it, then it will be a determinate form. Let's get to the first example of this type. It's gonna be the limit of 1 over x minus 1 over 12 over x minus 12 when x approaches 12. So I'll first have to deal with the numerator first because it contains the extra fractions, right? So I'm gonna subtract these two together. It's just gonna be 12 minus x over x, 12x, I mean, and then over x minus 12. Okay. And then I can rewrite the whole fractions. I mean, this big fractions over here as this, right? And then I'm going to switch the sign of the numerator. I'll have x minus 12. Then 12x times x minus 12. And now these two would cancel each other out. And I'll have an entire new function, which is going to be negative 1 over 12x. And then I will substitute 12 into this function. And it's going to be negative 1 over 144. The second example would not be much different. It is going to be finding the limit of 1 over x plus 8. And then minus 1 over 8 over x when x approaches 0. Okay, so I'll have to deal with the numerator again. I'm just gonna subtract these two together, the same as the previous example, and then I'll have 8 over 8 times x plus 8 minus x plus 8, and then over x, right? This thing as a whole. It's gonna be equals to, I'll calculate this one here right away. 8 minus x and then minus 8, it's gonna be negative x over these two just be x, 8x times x plus 8. And then x cancel each other out, x's, and I have negative 1 over 8 times x plus 8. Now it is easy enough because when I substitute 0 into the function, I will have negative 1 over 8 times 8, which is negative 1 over 64. The last example would also just be about simplifying the extra fractions. So it's going to be the limit of 2 over x squares minus 1 over 2 over x minus 2 when x approaches 2. Okay, so I'll just subtracting this one. Should be easy enough. 4 minus x squares. And then down in the denominator, I have 2x squares times x minus 2. And I will use the difference of squares formula here. 4 equals 2 squares. So it's going to be 2 minus x times 2 plus x over 2x squares times x minus 2. And then I'll switch the sign of this bracket over here. I'm gonna have negative x minus 2 times 2 plus x over 2x squares times x minus 2. These two will cancel each other out. And I'll have a very nice and clean function of negative 2 plus x over 2x squares. I plug 2 into the function, and I'll have negative 4 over 8, which is just negative 1 over 2. The final type of limit calculation that I think you most likely encounter is rationalization. For some functions that involve square roots, rationalizing it will help you to avoid the indeterminate form. First, to eliminate the square root in the numerator or denominator, or both, depending on which contains the square root, multiply both the numerator and denominator by its conjugate. You will realize that the pair of conjugates in the numerator or denominator of both can be changed by the difference of square formula. The square root will be gone when it's squared. Next, simplify the whole function, and again, it usually involves cancellation. And finally, plug a into the function. Okay, so this is the first example. Limit of square root of x minus 3 over x minus 9 when x approaches 9. So I find that the square root of x is in the numerator, and so I'll have to time both my numerator and my denominator with this one's conjugate. It's gonna be square root of x minus 3 and times square root of x plus 3 over x minus 9, and remember, you have to do the same thing with the denominator. And do you notice anything about our numerator right now? Yes, because this one looks exactly like the difference of squares formula, but in reverse. This is what you got after using the difference of squares formula, right? So I'll just reverse the whole process. Isn't the whole thing here in the numerator equals to this? That's right. And now you can get rid of the square root here. And it's just going to be x minus 9 over x minus 9 times square root of x plus 3. These two will cancel each other out. And you'll have 1 over square root of x plus 3. And it's going to be 1 over 6. Next, I have the limit of square root of 5 plus x minus square root of 5 over x when x approaches 0. Again, I have to tie both numerator and denominator with the conjugate of my numerator. The whole thing. So it's going to be square root of 5 plus x minus square root of 5 times its conjugate, which is square root of 5 plus x plus square root of 5 over x times the same thing. Alright, I will apply the difference of square formula, but in backward to the numerator. I'll have 5 plus x minus 5 over x times this thing. Okay, these two will just be equal to 0. X will cancel each other out. And what I have is going to be 1 over negative 5 plus, square root of 5 plus x, and then plus square root of 5. I plug 0 into the functions, and what I end up with is 1 over 2 square root of 5. The last example I have for you guys today is going to be the combination of rationalization and complex fraction. minus 1 over x. When x approaches 0. As you realize, these are two fractions instead of just one. It is just too complex, and I'll have to somehow manage to combine them into just one fractions. And in order to do so, I'll have to just subtract them. Just that. And it's gonna be 1 minus square root of x plus 1 over x times square root of x plus 1. And you see that both numerator and denominator have its own square root, right? However, only the numerator here has a conjugate. So I'll just time both of them with the conjugate of the numerator, which is 1 plus square root of x plus 1. I'll just use the difference of squares formula in backward for the numerator. It's gonna be 1 minus x minus 1. And it's just gonna be negative x over x times square root of x plus 1 times 1 plus square root of x plus 1. And negative x will cancel each other out, I mean x's. That leaves us with only negative 1 over square root of x plus 1 times 1 plus square root of x plus 1. Now that x down in the denominator is gone, you can just substitute 0 into the function, and I'll have negative 1 over 1 times 1 plus 1, which is negative 1 over 2.